Hi, everyone, and welcome to our module on tests of significance. Many clinical studies compare group means, and they often find differences between groups. For example, they may find different mean ages between two groups or differences in the mean blood levels between two groups. And the authors of studies need to compare these differences and determine how likely it is that these are real differences and not due to chance. And the way people often say this is, are the differences statistically significant? This is what we want to know. So in the next few slides, let me try to give you an image of what it means when the difference between two groups is statistically significant. Let's suppose we have group 1 down here and group 2 over here on the right in this chart, and they both have a bunch of test results. So all the patients in group 1 have results clustered over here, represented by these black dots. All the patients in group 2 have results over here clustered by these red dots. You can see from looking at this that it's pretty likely that the mean between the two groups is truly different. The mean of group 1 would be something like this, and the mean of group 2 would be something like this. The scatter in the data of group 1 is very tight around the mean of group 1, and the scatter in group 2 is very tight around that mean, and the means are very far apart. It's very unlikely that these two means are exactly the same, and we just happen to pick out a bunch of samples for group 2 that were way over here. It's very unlikely that's the case because you can see that most of the group 1 numbers are all clustered over here on the left around the group 1 mean. So when there's very little scatter of the data and the groups are far apart, it's more likely that the result is real and not due to chance. Now, as a medical student, you don't need to know the math of how these differences are calculated, but I want you to have a picture in your head of how far apart the data are when the differences between two groups are real. Now let's look at another example of group 1 and group 2. And once again, the group 1 mean is way over here and the group 2 mean is way over here. But you can see in this example that there's a lot of scatter of these data points. Look, here's a red point all the way over here. Here's a black one all the way over here. So the likelihood that the difference between these two groups is due to chance and that we just arbitrarily pulled out a bunch of red ones that happen to be grouped over here and a bunch of black ones that are grouped over here, the likelihood of that is actually fairly high because of all the scatter in the data. So when there's lots of scatter in the data between groups relative to how far apart they are, it's more likely that the differences are due to chance. So a key point is that the scatter of data points relative to the difference in means between two groups influences the likelihood that the difference is due to chance. And this is how differences between means are tested to determine the likelihood that they're different due to chance. You don't need to know the math. This is why we have statisticians. But just understand the principle that if your data set has data points that are all over the place, it's much more likely that differences between two groups are due to chance as opposed to when your data set has data points that are very tightly organized around the mean. Now let's talk about the number of data points. So here I've got group 1 on the left and group 2 on the right. And in this example, there is a fair amount of scatter of data, but I've got so many data points that it's becoming much more clear that group 1 really probably does have a mean over here on the left, and group 2 really probably does have a mean that's over here on the right. So the number of data points also influences the likelihood that differences between means are due to chance. If you have just a few samples, it's very hard to get the likelihood that the difference between groups is due to chance to be very small. But if you have a lot of samples, it's easier to get the likelihood that the differences are due to chance to be small. So I showed you all that to help you understand the rationale behind tests of significance. There are three key tests of significance that you need to know. These are the t-test, the ANOVA, and the chi-squared. And all three of these tests are going to determine the likelihood that the difference between two means is due to chance. And the likelihood that the test gives you is going to be based on the scatter of the data points, how far apart the means are, and the number of data points, all the things I was just showing you in those last three pictures. You don't need to know the math of how we actually quantify all this and turn it into a likelihood, but I do want you to appreciate the principle behind the science of these significant tests. So before we discuss the three specific tests of significance, we need to discuss types of data. The first type of data that you need to understand is quantitative data. And variables that are quantitative have numbers associated with them, like 1, 2, 3, 4. They go in order. They usually go from 0 up to infinity, and they can sometimes be negative. Other data are what's called categorical. So these are things like high, medium, and low, or positive and negative, or yes and no. So quantitative variables are often reported as a number. So for example, if they say the mean age was 62 years old, mean age is a quantitative variable. It goes from 0 up to 100 or infinity, and it's an actual number. Categorical variables are often reported as percentages. So they'll say 40% of patients take drug A. You can either be taking drug A or not taking drug A. You can only be in one category or another. This is not a quantitative variable, but they're giving a number to it just to help you understand the percentage. They could also say 20% of patients are heavy exercisers. You're either a heavy exerciser or not a heavy exerciser. It is a categorical variable, but they're giving you a percentage. And this is often a point of confusion for students. They will see percentages and think, oh, that's a number. It goes from 0 to 100. This must be a quantitative variable, but it's not. You have to pause and think about it. And the action of taking drug A is a yes or no action. Being a heavy exerciser is a yes or no function, so it is a categorical variable. And I point all this out to you because we use different statistical tests for quantitative variables versus categorical variables. So the first test of significance that we're going to discuss is called the t-test, and this is for comparing two mean quantitative values, and it yields a number called a p-value, and p stands for probability. And the p-value is the chance that the null hypothesis is correct. And this means the chance that there is no difference between the two means and that any difference we are seeing is simply due to chance. And if the p-value is less than 0.05, we usually reject the null hypothesis and state that the difference in means is statistically significant. Now, keep in mind, a p-value less than 0.05 doesn't mean there's 0% chance that the means could be the same and that the differences we are seeing are due to random chance, but it just means that it's low enough that we're willing to accept that risk. So let me give you an example of how this might come up in a board question. Suppose a researcher studies plasma levels of sodium in patients with SIADH and normal patients. The mean value in SIADH patients is 128 milligrams per deciliter with a standard deviation of 2. The mean value in normal patients is 136 with a standard deviation of 3. Is this difference significant? So common questions are, what test would be used to compare the means? And the answer is a t-test. How do I know it's a t-test? Because concentration of sodium is a quantitative variable. It's a number that can go up and down, 128 or 136 in the two groups. And then what p-value would indicate a significant difference between two groups, that would be less than 0.05. And remember, if the p-value is less than 0.05, it means there is less than a 5% chance that these two differences in means were due to chance alone and aren't differences in true mean values between the groups. So here's the same question stem, but now they ask you something different. They say, if the p-value is high and non-significant, why might that be the case? And the answer is because you need more patients. So remember what I showed you before. The more patients you have, the more confident you can be that the difference between the two means is real and not due to chance. So if you increase the sample size, you increase the power to detect differences. And I talk about power in another module on hypothesis testing, but the bottom line is that when you have more samples, you can be more confident that the difference in means that you are seeing is real. So anytime you get a non-significant p-value, you often need to go back and collect more data to determine whether or not you might actually have a true difference. Now let's talk about the ANOVA test, and ANOVA stands for analysis of variance, and you can think of the ANOVA as a t-test when there are more than two groups. It's used to compare more than two quantitative means. So suppose, for example, that we had a research study where they measured plasma levels of creatinine in non-pregnant, pregnant, and postpartum women. So there are three groups here: the non-pregnant group, the pregnant group, and the postpartum women. So you can't use a t-test when there are more than two groups. You have to use the ANOVA because we have three groups here. And the ANOVA test yields a p-value just like t-tests, and you can interpret it in a similar manner. And then the final test of significance is called the chi-square, and this is a test you have to use when you're comparing categorical variables. So you have to use this if the test results are not hard numbers. So the way this often comes up is you're asked to choose a statistical test for a data set. And when this happens, you have to carefully look at whether it's quantitative or categorical. And remember that slide I showed you a few slides ago where I went through quantitative and categorical variables. Beware of percentages. These are often categorical data. So for example, if they said 20% of patients in group 1 are heavy exercisers and 40% in group 2 are heavy exercisers, the way you test whether that's a statistically significant difference is by using the chi-square, because heavy exercise is a yes or no categorical variable. So I'm going to finish this module by talking about confidence intervals. And to understand this, let's consider an example. Suppose 16 normal subjects have their blood glucose level sampled. The mean blood glucose level is 90 with a standard deviation of 4. So the question is, what's the likelihood that the mean glucose of another 10 samples would also be 90? Or another way to look at this is, how confident are we in the number 90 milligrams per deciliter? In the scientific literature, means are usually reported with something called a confidence interval. So, for example, a study may say that among study subjects, the mean glucose was 90 plus or minus 4, and that plus or minus 4 is the confidence interval. This is saying that the authors believe that if the study subjects were resampled, the mean results would fall between 86 and 94, that's plus or minus 4 from the mean, for 95% of resamples, and for 5% of resamples, the result would fall outside the 86 to 94 range. So let's talk about where they get that number from. So to calculate a confidence interval, you need two things. You need to know the standard deviation of your sample data set, and we represent that by the Greek symbol sigma. And you need to know the number of subjects tested to find the mean value, and that's n. So the confidence interval is going to be plus or minus z times sigma over the square root of n. And z is almost always 1.96. Most people report the 95% confidence interval, and for 95% confidence interval, z is 1.96. If you want to do the 99% confidence interval, which is rarely done, you would use 2.58 instead of 1.96. So what you do is you take your data set, calculate the standard deviation, calculate the n, and plug it into this formula, and then you know what the 95% confidence intervals are. So let's go back to our example, and it says that 16 normal subjects were tested. So right away we know the number of subjects tested, it's 16. And then they said the blood glucose level was 90 with a standard deviation of 4. So they've given us the standard deviation. So we have all the things we need to calculate the confidence interval. And then the question asks, what is the likelihood that the mean glucose level of another 16 subjects would also be 90? Well, let's calculate the confidence interval. So that's plus or minus z times sigma over the square root of n. But remember, z is almost always 1.96, especially for 95%. The standard deviation is 4, and the square root of n is the square root of 16, which is also 4. So this is going to be 4 divided by 4. These numbers are going to cancel out, and we're going to get plus or minus 1.96, which is basically plus or minus 2. So our confidence interval is plus or minus 2. This means that there's a 95% chance that the next 16 samples would fall between the mean value of 90 plus or minus 2, which is between 88 and 92. So that's the way we can state our confidence in the mean value that we got from our sample set. Now let me make an important point here. Don't confuse the 95% confidence interval with the standard deviation. In the module on basic statistics, I told you that the mean plus or minus 2 standard deviations contains 95% of samples in a sample data set. That is very different from the mean plus or minus the 95% confidence interval. The mean plus or minus the 95% confidence interval says that we think there's a 95% chance that repeated measurements of the mean will fall within this range. So if you see them ask you for a 95% of something in a question stem, read it carefully for what they are looking for. Do they want to know the range in which 95% of your samples in your data set fall? That's the mean plus or minus 2 standard deviations. If they ask for the 95% confidence interval of the mean, then they're asking for this value right here. And make sure you understand the difference between those two. Now let me talk about some specific ways we use confidence intervals. And first I'll talk about when we use them with odds or risk ratios. So in the module on study designs, I talk about how odds and risk ratios explain the likelihood of increased rates of disease related to an exposure. For example, if you're exposed to smoking, does it increase your rate of lung cancer? And an odds or risk ratio of 1.0 means that the exposure risk factor is not associated with higher rates of disease. So some studies will report an odds or risk ratio with a confidence interval. And the key thing to remember here is if the confidence interval includes 1.0, then the exposure or risk factor does not significantly impact disease or outcome. This is easier to understand with an example. So let's suppose that the risk of lung cancer among chemical workers is studied, and the risk ratio is found to be 1.4 plus or minus 0.5. Well, that range of plus or minus 0.5 includes the number 1.0. This means that chemical work is not significantly associated with lung cancer. The formal statement would be that the null hypothesis is not rejected. I talk about this in the module on hypothesis testing. But the bottom line is if you're ever shown a risk or odds ratio with confidence intervals, check to see whether or not the confidence intervals include the number 1. If they include the number 1, then it means the exposure risk factor is not significantly associated with a change in disease rates. Another place where confidence intervals are important are in group comparisons. So many studies report differences between groups. For example, they might report the blood pressure difference between group 1 and group 2. You can average these differences and calculate confidence intervals. And the important thing to remember here is if the confidence interval includes 0, then there is no statistically significant difference between the groups. So let's consider an example. Imagine that authors of a study reported the mean difference between two groups is 1 plus or minus 3.0. Well, plus or minus 3.0 from 1 includes the number 0. This means that there is no significant difference between the two groups. This is very similar to saying that the p-value is greater than 0.05, or the formal way to state this is the null hypothesis is not rejected. So remember that anytime you see confidence intervals around a mean, look to see whether it includes 0. Another way that confidence intervals are important for group comparisons is if the ranges overlap. And the key point here is if the ranges of two groups overlap, there is no statistically significant difference. So let's suppose, for example, that group 1 had a mean of 10 plus or minus 5, and group 2 had a mean of 8 plus or minus 4. You can see that 10 plus or minus 5 goes from 5 all the way up to 15, and that includes the number 8 in the second group. So these confidence intervals overlap. And when this occurs, this means there's no significant difference between means. This is very similar to a p greater than 0.05 for a comparison of means. This is often shown in clinical studies in a chart. So imagine that we had the blood glucose level here along the x-axis, and then we've got group 1 right here and group 2 right here. What they will do is they will show you the mean represented by a dot, and then they'll put little lines out at the side to represent the confidence intervals. And then group 2 will also have a dot with little lines out to the side. Now, if these lines overlap, then the differences are not statistically significant. But if these lines are separated by some distance in space along the x-axis, then the confidence intervals do not overlap, and this means that the differences are statistically significant. So just to finish our example, imagine for a second case that group 1 had a mean of 10 plus or minus 5 and group 2 had a mean of 30 plus or minus 4. Well, you can see that 10 plus or minus 5 does not come anywhere near 30 plus or minus 4. These two intervals do not overlap. This means that there's a significant difference between the means, and this is similar to p being less than 0.05 for a comparison of means. And that concludes our module on tests of significance.